Hi everybody, this is Cal with sections 13.1, Vector Functions and Space Curves, and 13.2, which I believe is called Derivatives and Integrals of Vector Functions, or something like that. We'll get there in a minute. This is actually probably one of the easier readings that we have this term, so, just a slight breather here. So let me kind of go through these sections and point out what's important and what's not so important. So the main idea is that when you have a vector-valued function, a function that takes in a number and spits out a vector, we usually refer to this as R of t for a vector function, bold R, it's a vector. And it consists of three component functions for the three components of the vector. And you can express it either this way in bracket notation or over here with the IJK notation, and it amounts to the same thing. And really, everything that we do with vector functions is just going to involve looking at the three components individually. So take a look at example 1. It has an example of what are the component functions for a certain vector function. It talks about the domain of that vector function. And so, hey, it's pretty good basic stuff here. It talks about how to take the limit of a vector function. It's literally just the three limits of the three component functions, provided they exist. We're not going to worry about epsilon delta definitions in this class. Example 2 shows finding the limit of a vector-valued function. It talks about the definition of continuity at A, and it's literally the same definition that we had for continuity when we were dealing with single variable functions in Calc 1. So if you refer back to section 2.5, for those who still have your Calc 1 book, it's going to be a different section if you're looking at this ebook, and I'm not sure. Actually, I could probably tell you. It will be in section 1.8 if you're going from this book, and now I've lost my page. So that was ill-advised. Okay, so we're back to here. We were just talking about continuity. And so the book talks about the idea of space curves, parametric equations, parameters. It's all just language. Make sure you know what it means, and then move on. Examples 3 and 4 are about describing certain curves, sketching certain curves. These are good examples. These are things you should be able to do, and make sure you can follow what's going on here. Example 5 asks you to find vector and parametric equations for a line segment. It's just linking it to this idea of space curves. This is stuff that you already know how to do from section 12.5. And example 6 is a cool example. It's finding a vector function that represents a curve of intersection between two simple surfaces. Work through that example. It's a good one. It goes on to the next page here. I'm going to say we don't need to spend a lot of time or energy using computers to draw space curves, so you can really just kind of glance at, if you want to play with a computer here, it's a great idea. Wolfram Alpha is probably a decent tool that you could use. But you don't need to spend a heck of a lot of time and energy stressing about this stuff on the bottom of 867, or the stuff going on to 868. And that really just kind of ties up this section. So, I don't need you to reproduce the effects of computers in your head or whatever. So, computer stuff might help on your homework a little bit. I'm not going to say don't use it on your WebAssign, but you don't have to stress too much about the second half of that section. Moving on to section 13.2, derivatives and integrals of vector functions. Really a very, very straightforward section. And what it kind of amounts to is that to take a derivative of a vector function, you take the three derivatives of its component functions and move on with your life. What I want to highlight here is on the top of 872, this idea of tangent vectors, tangent lines, unit tangent vectors. This one's going to come back to haunt us a few times in the next section, so make sure you know this formula for the unit tangent vector. Think about how you would use a tangent vector to find an equation of a tangent line, which is kind of covered in this paragraph, but spend a thought on it, figure out how it might go. And example 1 and 2 and even 3 kind of go through those concepts with some concrete examples. The second derivative of a vector function is what you think it is. And then it talks about differentiation rules. Spend a little bit of time thinking about rules 3, 4, and 5. These are all versions of the product rule that you're used to. And whatever kind of product you're taking, be that a scalar function times a vector function, you have the product rule showing up here the way you would expect. If you have a dot product of vector functions, the product rule works the way you expect with dot products, replacing whatever kind of product you're using. And same for cross products. Also pay attention to the chain rule as it shows up in number 6 over here. So these are actually valuable differentiation rules. Example 4 is a good example. I like it. Work through it. And then we talk about integrals of vector function, and again, they are exactly what you think they're going to be. Example 5 demonstrates how it works, and that's it for this section.